record from now?
I started already, so just end it.
Sure. But don't worry.
Jeff, you.
Sorry, again.
Lowry? Lowry? All right. Albury? Okay. Eric Cunningham. Adam Meduccio. Sudni Patel. Sudni Patel. Hong Yu Wu. Faiz. Sudni. Okay. All right, I'm just going to go through the midterm, sort of problem by problem. If you have any questions, just let me know. So problem number 1 was very much like one of our homework problems. A little different. This was our circuit. It's an RLC circuit, and we want to determine state space and output equations for the system. Okay, so a couple things to remember. Always remember Eli the Iceman, and that we want to determine states of the system. The easiest way to do this is currents through inductors. Voltages across capacitors. Okay? If I do that, then we can do two state equations, one using Kirchhoff's voltage law for x1, one using Kirchhoff's current law for x2. Right? Kirchhoff's voltage law because inductors, Kirchhoff's current law, because capacitors are defined by current. So, Kirchhoff's voltage law going around this mesh, it's negative U of t plus L di dt, so that's going to be 1 over 10 x1 dot. And then I have to do the voltage drop across this capacitor. That voltage drop is going to be x2, right? x2 is the same voltage drop across that resistor. So plus x2 is equal to 0. So the next one is going to be Kirchhoff's current law. We'll say that the currents entering that node are all going to sum to 0. So what are the currents entering this node? Well, one of them is going to be x1. The other one is going to be the current going through this resistor. V is equal to IR, right? So current is going to be V over R. It's x2 over 100. That's going to be negative because I want the current going into the node, okay? And the last one is going to be the current going across this capacitor. I is equal to C dV dt. So I'm looking for negative C dV dt. That's equal to 0. Okay? And then the last one is just my output equation. My output y is just equal to x2. So if I want to be more, I guess, formal about how I write this, I'm going to solve this for x1 dot. So this would be x1 dot is equal to negative 10 x2 minus 10 u of t. This one will be x2 dot is equal to 100 x1 minus x2. Okay, and once I solve for the change in x1 and the change in x2, then I can just go straight into my, let's not do it that way. Well, maybe we will. Okay, and then we just have to fill in those A, B, C, and D matrices. Okay, so x1 is negative 10 x2 minus 10 u. x2 is equal to 100 x1 minus x2. Y is just equal to x2. Any questions on part A? Okay, so part B says find the transfer function. The easiest way to go about this is to just convert everything into impedances. So if we take everything into impedances, circuit will look something like this. Remember, Inductor gets multiplied by S, so it's S times L, so it's going to be SL over 10. Resistors stay the same. And it's 1 all over SC. So 1 all over S divided by 100. We got 100 over S. Okay? This guy's a parallel combination of impedances. So we'll call this R. It stands for resistance. Let's call it Z. So Z is going to be parallel combination of impedances. You multiply the numerators. You add them in the denominator. Seems weird to me. No, that's right. Okay. So if I multiply everything through, that's not right. By S over S, I get that. And then if I simplify it, I'll get, this looks weird. This is right. Okay, so this parallel combination Z is just 100 over S plus 1. So then to find the voltage across this parallel combination, it's a voltage divider, right? This voltage is going to divide it up over this voltage and that voltage. So Y of S is going to be equal to this impedance, which is 100 all over S plus 1, divided by the total, which would be S divided by 10, plus 100 all over S plus 1. And that all gets multiplied by voltage divider, right? Now I just need to simplify. So excuse me. So if I divide my output over my input, that will give me my transfer function, which is what we want to find. So I can multiply all this stuff through by just trying to simplify stuff out. So let's take multiply everything through by S plus 1 over S plus 1. Get something that looks like that. And then let's multiply everything through by 10 over 10. And then if I simplify, I get 1,000. That should be my answer. Questions on part B? So number 2. Consider a certain description, or a certain system described by okay, this is a differential equation. All right, I can take that differential equation, immediately And take the Laplace transform of each of the terms. Why can I take the Laplace transform of each of the terms separately? Because it's a linear operation. Okay, so now that I got it in terms of Laplace, I can take and isolate my output y. And I can solve for y all over u, which is my transfer function. And then if I try to factor this, be s minus 3, s plus 3, s minus 1. So part B says, what's the impulse response? So to find the impulse response, I have to do a partial fraction expansion because our Laplace transform tables don't give us an answer for something that's complicated. So if I solve for A, it's just going to be s minus 2 all over So if I solve for a -3 here, it'll be -5 over -2. No. S minus 1. 5 over -4. Solve for B. Put in 1, I get -1 all over 4. Just -1 over 4. Okay, so if I put that back into my partial fraction expansion, I can go immediately to my Laplace transform tables, and it becomes an exponential. That is the impulse response of the system. Questions about number 2? Okay, so here's a state space representation of an LTI system. We're going to develop an op-amp circuit. Okay, first thing we need to do is break down the state space equation into some simpler forms. So we've got x1 dot x2 dot we have our output. Okay, but remember, when we use an op-amp circuit, we always use inverting op-amps. So I could solve this for negative x1 dot Okay, and once I've solved for the negative of everything, I'm able to just start constructing my circuits, because now I've got the weights of each of my states correct. So for x1, we're going to have an integrating amplifier, and now we just have to determine what the inputs are. So it's immediately negative x1, so he's going to go into, sorry, he's going to go into an inverter.